Hi, this is Adam Ward. I want to work through the last exercise from Lecture 5 in Surface Water Quality Modeling. In this exercise, we pick up with our same chain of 3 lakes in a row that we explored in feed-forward systems, but in this case we're going to also consider these with a new feedback process added, by which 50% of discharge from Lake 3 is recycled into Lake 1. So each of our 3 lakes still has a distinct load. We have discharge into the upstream lake that cascades through the system. And newly added in this problem is the feedback, in which 50% of the discharge that goes into or out of Lake 3 is recycled back to the beginning. So let's think first about what this means for us in terms of discharges before we move into the problem. Well, as an input, let's assume we still have our 3 times 10 to the 6th cubic meters per day that flows into Lake 1 from upstream, and then of course it would cascade into Lake 2, Lake 3, and further through the chain. Now the wrinkle we've added here is 50% of that incoming discharge gets recycled back from Lake 3 to Lake 1. That's the blue arrow with the red box that's around the 0.5 times Q23 at this point. So 50% of that discharge in would be 1.5. So if we assume that 1.5 is flowing back, that means the discharge out of the first lake must also have an additional 1.5 times 10 to the 6 cubic meters per day. If it flows into Lake 2, it must also flow out of Lake 2, so that value goes up. And at the end of the day, that 3 cubic meters per day that came in the very upstream end goes out the very downstream end. So there's just some internal recycling that's going to happen. Moving forward from this point, we're still going to simulate reactive losses in each lake, and now we're also adding a settling loss into each of our lakes in the system. So what I'd like to do next is work through the steps to solve this problem. The first step will be to write out the complete equations for each lake in the chain. So for lake number 1, we've got the volume of the lake times the time rate of change of concentration in that lake equal to the loading W1 plus the inflow from that recycled water, and we've got an outflow, a reaction loss, and a settling loss. Now this fits our general pattern for describing these systems, in which our accumulation on the left-hand side is balanced by the loads into the lake and the removals from the lake. That's the complete equation written out for lake number 1. The equations for lakes 2 and 3 in the system look fairly similar. So we're accounting for all of the same processes in both of those lakes. And we'll pause here and just give you a moment to catch up on writing if you're following along in real time. Now before we move on, I'd like to just point out a couple of things that are unique in our feedback system. Every outflow that's associated with a discharge has to be an input somewhere else in these feedback systems. So for example, you can see what I've highlighted with the orange arrows here. Discharge out of 1 into 2 becomes a load to Lake 2. Discharge from 2 to 3 becomes a load in 3, and the curved orange arrow represents that recycling of water from Lake 3 back up into Lake 1. So those arrows that are pointing top right to lower left are examples of feed forward, and that curved arrow is an example of the feedback mechanism that we're considering here. So moving on in our solution, we're going to assume steady state. That means that we can zero out those derivatives. The dc dt terms become 0. Concentration is no longer changing with time. And by doing so, we can rewrite these equations and reorganize ourselves just a bit. Now what you'll notice as I'm writing these equations out is that I've gone ahead and grouped terms so that everything is multiplied by a concentration. So I've grouped all the coefficients for the C1s, C2s, C3s, and so forth in each equation. Looking at our steady state equations, the reason I've written them this way is that the assimilation factors fall out very nicely. And as we move forward into a matrix solution, it seems like a good idea to write our terms this way. When I need to calculate a value for A11, I know exactly what those coefficients are. I don't have to go hunting through a complex set of equations for them. I'd like to point out just a few more features before we move on here. One is that some of these coefficients are zero. Right? I've added a zero even though that coefficient did not exist anywhere else. The one that I've highlighted in green for you is specifically telling us that a load into 3 has no direct impact on lake number 2. Now, your gut check should tell you that's true. There is no arrow from lake 3 back into lake 2. So it's not surprising to us that that should be zeroed out. The second thing that I want to point out to you has to do with the signs in this equation. So once we zeroed out the left-hand side, we moved all of the terms that were not direct loads. Everything that's not a W got moved from the right-hand side to the left-hand side. The consequence of doing that is all of the signs in the equation change. So I'm using this light green color to point out just a few of those. Negative terms became positives, positive terms became negative. This is a really common mistake that people make when they try to just simplify those complete equations and not rewrite them again. People forget that those terms change, and so they end up with the wrong signs, and consequently they'll also end up with the wrong solutions. So we've written our equations, we've simplified them for steady state, we've grouped terms to make our life easier for a matrix-based solution, and on the next slide we're going to actually formulate the matrix solutions for this problem. So as we discussed in lecture and as you've seen in the text, the general form of our solution is going to look something like this, where we have a matrix that includes all of our assimilation factors multiplied by a concentration matrix equal to our forcing. When we put our numbers into this matrix, these are the solutions that I find for each term. And on the right-hand side, I've got the loading for each lake, so 26, 10, and 15 kilograms per day. So now we've formulated the problem, what's left is to actually solve it. So step 4 is going to be to solve for the concentrations. Our general solution here, or our general strategy I should say, is that our concentration matrix is going to be equal to the inverse of the A matrix multiplied by that loading matrix. So what you see on your screen right now are my numerical solutions for this. In terms of how we get from the matrix of assimilation factors to its inverse, that's something that I'm going to suggest you not attempt by hand, although it's possible. I've tested this solution using both MATLAB and a web-based tool that does matrix inversions, where you just type in the numbers and click invert. That's written in JavaScript. So I suggest that's a tool that you might use. There's a link in your homework 2 assignment to some of the web-based tools that I've tested thus far. From here, it's a simple matrix multiplication. Again, you could do this by hand, rows multiplied by columns, and then sum those terms together. Or you can use your favorite tool, be that MATLAB, Mathematica, or again, I've also tested this with a web-based tool and provided that link in your homework assignment. So when I solve this for concentrations, the values I get are listed out on the right-hand side here. If you've been following through units from the beginning, these are in kilograms per cubic meter. The top entry is the first lake concentration, the second lake, and the bottom entry in that matrix is the concentration of the third lake. Now, we're not quite done yet. We missed one item from the exercise assignment here, which was asking us to use this matrix inverse to determine how much of the concentration in lake 3 is actually due to the loading in 2. So essentially we're asking, how does a load in 2 get translated into a concentration in 3? Now, to solve this problem, we can take advantage of some of the terms that we've already got in our equation. So A32 is the response of lake 3 to a load in lake 2. We can multiply that by W2, the load into that lake. And so I'm just grabbing that appropriate term out of the inverse matrix, multiplying by the loading, and I get 2.1 times 10 to the negative 8th kilograms per meter cubed, or into units that are perhaps a little easier for us to wrap our heads around, 0.021 milligrams per cubic meter as my final solution. I hope this narration was helpful. If you're still challenged by this, there's a very similar example in your textbook, example 6.1. I'd suggest that you check out that explanation as well. Thank you.